Okay, gang. So to round out our time doing benzene, electrophilic aromatic substitution things, I just wanted to do one more example that I think, I'm not saying it's crazy hard, but I think if you can, look at this, understand it, handle it, then you have a pretty good holistic idea of all the kind of concepts at work. Okay? So let's see what we got going on here. We have 4 steps, which anytime there's, multiple steps over a reaction arrow, it's really easy to get, scared, maybe a little anxious, but if you just stay calm, take a breath, and then just take it one step at a time, right? There's no reason to rush. It's like learning to fly, or falling in love. Just kidding, none of those things. However, if you just take it one step at a time, before you know it, you have your final answer, okay? So, let's take a look at what we got. If we just block this out and look at our first step, well, it looks like we have an acid chloride and we have AlCl3. So this is screaming to me Friedel-Crafts acylation, right? So it just looks like we're gonna stick this carbon onto our structure. So I'm gonna go ahead and just kind of do my work down here, okay? I'm gonna use this double bond and I'm just gonna stick my thing right here. And I make sure 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Cool, I didn't lose any carbons. So I think that is what step number 1 is. Okay, so step number 2. Okay, so this would be the same if we were gonna do, Clementon reduction, something with Randy nickel. What this is gonna do, right, we have a hydrogenation. It's going to reduce, any benzylic carbonyl carbons, or any benzylic any benzylic carbonyls we have. It would touch any other alkene bonds that we have in the rest of our structure, but we don't have those. Specifically, we're gonna just reduce this down and we're gonna lose our carbonyl at the benzylic position. Okay, cool. We'll move over here. So for step 3, okay, so this is a little callback to OChem 1. We have a secondary carbon right here, and we see our good old friend potassium terbutoxide, and a polar aprotic solvent, right? Because DMSO looks like this, kind of like acetate, but not really, with the sulfur. So this is screaming, this is screaming to us that we are going to, polar aprotic solvent. So this is screaming to me E2, but not just any E2, right? It's E2, but we're gonna get the Hoffman product. And remember, the Hoffman product is we're gonna make the least substituted carbon, not the most substituted carbon. So we're gonna do E2, but instead of making our double bond between the secondary and secondary carbons right here, we're gonna use secondary primary. Oh, sorry, we lost that. We don't have that anymore. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Double bond right there. Perfect. Okay. So now, on step 4, what do we have going on here? So we have H2SO4 and just water. So kind of a confusing, vague step almost. But don't lose your cool. You have knowledge. You have your organic foundations to fall back on. If anything, we have a strong, strong acid. And we're not ever going to touch the bonds inside, right? Because this step doesn't involve any of the catalysts that we've been using to work with the bonds inside benzene, right? So we do have one double bond that's outside the ring. So why don't we just try protonating that and see what happens? So I'm going to go ahead and just kind of draw sulfuric acid. Let's see what happens if I would protonate this. Didn't touch anything inside the benzene ring. Okay, so I have a choice of making a carbocation here or here. Clearly, I'm going to do secondary over primary, right? I don't have any like allylic situation, benzylic thing going on. I'm just going back to my carbocation forming principles. Okay, great. So now what do I do? Well, remember, we're dealing with Electrophilic aromatic substitution. Electrophilic, something that likes positive stuff. And that's our benzene ring. Well, wouldn't you know it, we just made something positive and we have this benzene ring. And the group we have attached here, we know alkyl groups are ortho-para-directing, right? So if you think about it, maybe this carbon or this carbon, right, these two are the same, want to attack here. Now if you think about it, this carbon is 1, 2, 3, 4, 5, 6, 7, 8. That would, if we attack this way, we would form an 8-membered ring. That's a little too big. So let's look at that's the ortho, or the para position. Let's look at the ortho position. 1, 2, 3, 4, 5, 6. Bing, 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 bing. 6-membered ring, right? Because if we just take this bond right here and attack, if this is carbon 1 and this is carbon 2, 3, 4, 5, and 6, right? We're gonna close our ring and we're gonna make the best ring we can possibly make, a 6-membered ring. So let me draw this down here. So let me even do this again. 1, 2, 3, 4, 5, and 6. And see, I have a methyl group off of 6, right? That was just part of what I came in with. So there's my structure, and remember, I mean, I'm not really drawing a mechanism here, but I'll go ahead and finish the mechanism. Since this carbon gained a bond, I lost something right there, so I'm gonna go ahead and erase my little miniature 2. There's a carbocation right on this carbon, right? But I can have a cleanup, right? This is just like the rest of our EAS mechanisms. So if I have a hydrogen right there, I can have the conjugate base of this come back in, do the deprotonation, regain my aromaticity. So our final answer here is this. So be careful, guys, because I've seen this in a lot of problems. It's a very popular way to kind of wrap in like and kind of a disguised EAS, but it still very much falls under, you know, fulfills the definition of what an electrophilic aromatic substitution is. Yes, we're used to seeing the stock reactions we've been working with. Friedel-Crafts alkylation or acylation, right? The sulfonation, the nitration, the bromination, the chlorination, right? However, there's nothing else from just having a benzene ring knock into something that's positive, right? And not only is it something positive, right? It's intramolecular, right? So this is very popular because intramolecular reactions are always great, right? Because it doesn't affect anything bad with entropy. Your reactant, your nucleophile, your electrophile are within the same. So just be careful if you ever run into a situation maybe where you have some type of double bond dangling in your structure and maybe there's some acidic step, because that's someone trying to say, hey, by the way, we can protonate this and then your ring is going to be interested in attacking itself. Okay, guys, hit the practice and hit it hard. This is our last video for the EAS related things. Just don't forget, we picked up some new knowledge, you know, along this section, but you saw like right here, the old stuff doesn't go anywhere. Okay, gang, I'll see you in the next video.